Alright, so this is going to be 7.2, this is part 2. Part 2, where we're going to be discussing permutations and combinations. So before I just tell you what permutations and combinations are with the formula and everything, just throwing it at you all at once, I'd first like to motivate these things with a couple examples. So I'm going to make up a couple scenarios here. So let's say it'll be sort of similar to examples I've given before, but let's say you are buying a pizza, and let's say you already know what kind of crust you're getting, what kind of sauce and cheese you're getting. That's already been decided. So you're trying to decide what toppings to get. Let's say for whatever reason you want 3 toppings. Maybe you're using some coupon, because who really orders pizza for delivery without using a coupon, right? You know, they got coupons online that you can use. Anyways, so you're using maybe some coupon that only lets you get 3 toppings. You want 3 toppings, and the store offers, let's say you count up all of the toppings, let's say 15 different toppings. And here's the question. How many possible choices do you have for toppings? I need to add a condition to this. Oops. Okay, the condition I need to add is that, I'll just say parenthetically, let's assume that you will not, this is an important point, will not repeat any toppings. Now, you may say, well, I already know how to deal with this. I can set up like, 3 blanks for my 3 different categories of toppings. And since I don't want to repeat toppings, I'd have 15 choices at first, then 14 for the second choice, then 13 for the last choice. But I would say that's not completely correct. So, and why is that? So, in red here, I will say this technique, where we would say 15 times 14 times 13, which is what we used in the first part of 7.2 to count up things when you're not allowed to repeat, right? So you have 15 choices for toppings in the first position, then 14, then 13, and you may say, yeah, sure. This technique, though, does not work in this case. Why? Because the order of the toppings is not important. So because this is very subtle, it's a very subtle thing, I want to point out the example I worked out with the pizza restaurant from 7.2 part 1, and I want to point out why it's different. So this one from the previous video says, how many choices are there for a pizza at a restaurant that has 2 choices for crust, 3 choices for sauce, and 3 choices for toppings? And I said, I used this technique where we said, okay, 2 choices for crust, 3 choices for sauce, 3 choices for toppings, and I took the product of them and got an 18 total possibilities, and I even drew a tree diagram there. You may recall that I made a point about these things all being unique, right? All 18 of these are unique combinations. And so what's the difference here? What's the difference? In this and this? Well, one of the differences is that each of these in this problem, each of these categories is it's really its own category, right? Like type of crust, type of sauce, and type of toppings, right? Whereas here I'm talking about one single category. It's much larger, 15 toppings, right? So they're like in their own category. And one of the big points here is that the order in which you place the toppings on the pizza doesn't matter, right? It's not important. We're assuming it's not important, right? Like pepperoni, sausage, mushroom is the same as sausage, pepperoni, mushroom, which is the same as mushroom, pepperoni, sausage, etc. Right? It doesn't matter what order you place them on the pizza, right? Unless you're really, really picky, but we're pretending, right, that we're not, and the order is not important. So it's not the same kind of problem as this one. Okay, it's just not. It's a different kind of problem, and it is subtle. I'll give you that. It's a subtle difference, and it takes some practice getting used to. In fact, I had to pause the video for a second and say, "Wait, how is this different?" And it takes a little bit of practice. But the key things to note here, key characteristics of this type of problem, is what we're looking at is order does not matter. And repetition is not allowed. Repetition is not allowed. Okay. So how do we deal with this? So how do we count this then? New technique. We need a new technique. We need a new, a new technique. Okay. Before I outline this technique, I would like to give you another problem to contrast with this one, which will also require a new technique, and then we will write down what these new techniques are. So let's say, here's the question. In how many ways can gold, silver, and bronze medals be handed out to, to the winners of, I don't know, a race, if there are 15 participants. All right, what are the sort of defining features of this one, of this kind? And you'll notice the numbers I've picked are the same, right? there's 15 different toppings, 15 different participants. We want 3 toppings here, and up here there are 3 medals to give out. So at least the numbers are the same. The context of the problem is very much different, right? What is one of the key differences, other than it's a different word problem? What can I say here? Order does matter, right? And, well, before I say and, why does order matter? Well, because giving John, Bob, and Sally medals, if gold, silver, bronze, the order very much matters for who gets gold, who gets silver, and who gets bronze, right? Like the triple of John, Bob, Sally is different from Sally, John, Bob, right? The order of who's up on the podium getting gold, silver, and bronze matters. It matters to those people, right? Whereas over here with the pizza, it doesn't matter what order you put the 3 toppings on the pizza. You could do pepperoni, sausage, mushroom, or mushroom, pepperoni, sausage, or sausage, mushroom, pepperoni. Those are all the same thing, right? But here, the order does matter. The order does matter for this problem. Oh, and we know repetition is not allowed. Now, in the last problem, I just told you straight up that you weren't going to repeat toppings, but how do I know repetition is not allowed in this problem? Well, because you only have 1 gold, 1 silver, and 1 bronze medal, right? So you can't give out 3 golds, you can't give out 3 silvers, you can't give out 3 bronzes, you can't give out 2 of any of, there's just 1 of each. So these are going to be 2 new types of problems that required new techniques, new counting techniques. This is a permutation. This is a permutation problem. That's a crazy looking P there. This is a permutation problem. And back here, which is similar, except that order does not matter, this is called a combination problem. All right. I'm going to define them officially for you using the definition that the book gives, and then we will talk about some defining features that maybe these definitions leave out, and then I will do the math. All right, a combination involves choosing a specific number of objects from a particular group of objects, so like picking 3 toppings from a group of 15 toppings, using each only once, so that's a critical defining feature here, when the order in which they are chosen is not important. That is arguably the most important defining feature of a combination. Okay, a permutation involves choosing a specific number of objects from a particular group of objects, using each only once. So far exactly the same as combination, but then here we go, here's where they are different. When the order in which they are chosen is important. So something I'd like to say here is that when you're asked to give rankings to something like first, second, third, or like president, vice president, or gold, silver, bronze, stuff like that. So rankings is a good thing to be on the lookout for when you should be using a permutation. All right, so now I'd like to write the formulas for these things. So I'm going to use some colors to line this up. So we have the calculation for combination with r number of things, so r is a number of things chosen or picked from a group of n number of objects. So n is the bigger number, the overall group number of objects. And that's going to be what color did I use over here? Blue. Little n, capital C, little r. That's like the way to notate this. NCR. It's going to be equal to, remember I told you we would need the factorial math, right? Well, here it comes. It's n factorial divided by r factorial times the difference of those two numbers factorial, n minus r factorial. Okay. So we're going to come back to the pizza problem and do that calculation, but let me write down the calculation for permutations. So with r number now, let me say something. Maybe instead of saying r number of things chosen from a group of n objects, maybe I should say, just to be a little bit more precise in my verbiage, or just to be a little less misleading, I suppose, I could say r number of things ranked, right? Because that's what a permutation does. It like orders things, right? It won't always necessarily be specifically ranking things, but like the order matters. So maybe you could say r number of things ordered instead of chosen there. Okay. And what is the formula going to be? Well, we denote it by NPR, not the radio station, just formula here, and it's just going to be n factorial. It's very similar, but it's not, it doesn't involve the extra factor of r factorial here. It's just going to be n factorial over n minus r factorial. So let's now go back to the previous problems and actually solve them. Okay, so we have this pizza problem. We now know that we are taking 15 things and we're choosing 3. We're choosing 3 from the group of 15. So recalling that this technique was not right? Let's see, what do we actually get? Well, not NCR, but 15C3, right? These are my numbers here. These are my numbers. The group size is, here, let me do this. The group size is 15, and I'm picking 3 things. So n is playing the role of 15 is playing the role of n, and 3 is playing the role of r here. So I'm going to have 15 factorial over 3 factorial times 15 minus 3 factorial. So this is very much similar to problems I worked at the end of the last video, right? Just looking at those factorials. And what are we getting here? So let me do that difference first before I start expanding these things. So 15 minus 3 is giving me 12, still with that factorial symbol attached. And now if you're comfortable with the way I dealt with those problems previously, these factorial problems, you know that what's going to happen is so there's all the 15 factorial, right? And I'm just kind of scooting the 11, 10, 9, 8, 7, 6, 5, 4, 3, 2 all under the rug, and just putting dot, dot, dot right there. 3 factorial is 3 times 2. And then times, so there's the times connecting 3 factorial. Technically, there's a multiplication right there. There it is. And then 12 factorial. So if you've watched that video, you already know what's going to happen is this 12 factorial completely cancels with all of these terms. So I just end up with a 15 times 14 times 13 over 3 times 2. Now remember that I said back here, this technique does not work. Oh, sorry, I'm trying to get it all on one page. This technique here did not work for this problem. But look how close it gets, right? I mean, we have 15 times 14 times 13 over 3 times 2. So what's happening here? What's the difference? Why is this divided by 3 times 2 there? Like, what is the difference? What does this not account for? Because this is the technique we would have used kind of naively without thinking about this new technique of combination. So what is happening? It's the order of the toppings not being important that's happening. This here, dividing by 6, because that's what 3 times 2 is, takes care of those things that we don't want to double count. So this divided by 6 takes care of things like this, like having pepperoni, sausage, mushroom being the same as mushroom, sausage, pepperoni, being the same as sausage, pepperoni, mushroom, and etc., right? These should all only count as one choice. And this magical little combination thing makes it so that we don't double count or triple count or quadruple count things that we don't want to, we only want to count once. That's what this division by 6 does here. It's very nice, right? We're not going to talk about like the behind the scenes magic of this, partially because I would need to do some research on my own to really to be able to explain it well. But also it's just like outside of the bounds of what we want to do for this class. But it is very, very powerful in that it takes care of all of that repetition for us. It cleans it all up for us, as long as we follow through the formula right. And by the way, what does this equal? I have no idea. Let's just go ask the calculator. 15 times 14 times 13, and then divide that by 6. I get 455. Okay, that is the answer to this first pizza question. How many possible choices do you have, assuming that you do not repeat any toppings? 455. All right, now the other one was, oh, wait, here it is. Nope, where is it? Here it is. This one. So order does matter here. So we're going to use a permutation. Sorry, let me get my stuff out of the way here. All right, a permutation. So we're going to have 15p3 instead of c, because this is a different kind of problem because order does matter. And that's going to give us 15 factorial over 15 minus 3 factorial. So it's slightly different, right? It doesn't have that extra factor in the bottom. And this ends up giving us 15 factorial over 12 factorial. And that's just going to, so I encourage you to write these out. 15 times 14 times 13, etc. And in the bottom, 12 times 11 times 10, blah, 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 etc., all the way down to 1. You'll see all of those things canceling, the 12, the 11s, the 10s, the 9s, etc. And you'll just be left with this. This is what we were thinking with the pizza problem when we assumed that order did matter. When we naively assumed that order did matter, this is exactly what we get. And that's exactly what the permutation gives you. So sometimes your intuition So with these permutations, right? With these permutations, your intuition can sometimes guide you there, especially if you're real good with the techniques that we used in 7.2 a bit earlier, like 7.2 part 1. Because you might have said, oh, let me calculate this for you just so you can go ahead and write it down. This is 2,730. 2,730. But if you fell back on techniques from 7.2 part 1, you may have said, well, there are going to be 3 winners, right? Gold, silver, bronze. And I only have 3, I only have 1 of each medal. So first choice, I have 15 people to choose from for the gold medal. Then there would be 14 for the silver medal, because 1 person has been used up. So, well, what I mean is they've already received the medal, and you can only receive 1 medal. And then there would be 13, because 2 people have received medals, so now there's 13. And you would not have been wrong. So a lot of times, permutations, you may think that you may say, like, do they even need their own fancy formula? Because our intuition can get us there. If we have good critical thinking, problem solving skills, we can get there just by using this method, which we've already practiced a bit, right? So in answer to that, I would say you have a point. You have a point. Maybe permutations don't need their own formula, but it really is useful. Anytime in math, relying on intuition, if you have good intuition, that's great. But also, you like to have a formula to fall back on, right? It's always nice, to have to have some kind of rigor from math to fall back on when your intuition fails you. So, hence, we will continue to use the permutation formula, even if you say, well, I think I don't really need it. All right, let's look at some examples. All right, what I'd like to do now is I'd like to work problem sets 36 through 34. No, 36 through 44 in the text. Because these specifically say determine whether each one is a permutation or a combination. And I feel like that these are really good problems to look at. One of the hardest things about these permutations and combinations is deciding when to use each one. Like, when does order matter, when does order not matter? Because these problems are given as word problems. So you've got to be able to read the word problem and pull out this information of whether or not order matters or not. So I'd like to practice that a bit. So what you should do now is go ahead and open up the ebook in Hawks, pause the video, go get the ebook open so you can see these problems, because I'm not going to write the problem out. I'm just going to read it. All right. And also, I'm going to skip the couple that I've assigned in this section for review, so to give you a chance to try a couple on your own. Okay, so 36 says, there are 10 board members on the Community Arts Council. In how many ways can a president and a treasurer be chosen? Assume that no member can hold both positions at the same time. Alrighty. All right. What do you think? Does order matter? Does order matter? If you pull 2 people from your group of 10 people, you got Bob and Sally. Does the order matter whether it's Bob Sally or Sally Bob? Well, you may say, well, I don't think so, but think about this. The positions are unique, president and treasurer. So Bob being president, Sally being treasurer is different than Sally being president, Bob being treasurer. So order does matter. Order does matter here. Think of, you can sort of think of president versus treasurer as like first versus second place. Whoops, first versus second place. maybe that's, I don't know, like president, vice president kind of thing, first and second place. So order definitely matters. And by the way, what would the calculation look like? Well, there's 10 people, so 10, and it's a permutation because order matters, and then we're picking 2. So that's going to be the calculation, or at least that's what it looks like, and then the actual calculation would be 10 factorial over 10 minus 2 factorial. So that's 10 factorial, which is going to end up being 10 times 9, which is 90. And I'll let you fill in the details, or you can always ask me in class too, the details, the arithmetic going from this step to this step. And again, though, you see it's very much like, the way we would have solved this prior to learning this permutation formulas. You would say, oh yeah, there's 2 positions and there's 10 choices for the first person, then 1 person has been taken, so now there's 9, and that's 90. So it's okay to think about it that way too, but make sure that you also understand the line of reasoning, how we got to order mattering, and then meaning that in turn means that we're using a permutation. 37 says, in how many ways can a committee of 5 people be chosen from a pool of 120 employees? Well, there's no ranking to the 5 people. It's not like president, vice president, treasurer, secretary, whatever. There's not rankings, right? It just says 5 random people, or 5 people from 120 employees, so order does not matter. That means we're using a combination. What are the numbers? Well, the group, we're picking 5 from 120, so it'd be 120 C5. That's how we would write it down. By the way, some of your calculators probably have these buttons on there, and you can, in fact, so here's my calculator that I've been using since, I don't even know when I bought this, like 10 years ago at least. So how do I do this? My button, it says PRB. Right there, that's the button I'm going to want to use. So how would I do this calculation? I would say 120 for 120. I would hit this button and then go over to, see, there they are. Can you see that with that light? NPR, and I want NCR. Oh, look, there's also just a plain old factorial. Okay, so I want NCR, then we hit equal, and then it lets me type the second number, so 120 is the N, and then the R is 5, and it calculates it for me. Calculates it for me without me having to actually write it out. So I'm getting 190578024. All right, I want to talk a little bit about why something like this might be important. Oh, and how do you do this without a calculator, or if you don't know how to do it on your calculator or whatever? So we would say 120 factorial over 5 factorial times 120 minus 5 factorial. That's going to be the same as 120 factorial over 5 factorial times 115 factorial. From 120 minus 5, there's 115 factorial. And then 115 times 114 times 113, all the way down to just times 2 times 1 would cancel out with most of this. So I'd be left with 120 times 119 times 118, all the way down to, 117. And that's it, right? The rest of the string cancels with this down in the bottom. All of those cancel, but I still have the 5 factorial. The 5 factorial sticks around. And now I would have to reduce this. I could play around with the fractions. I know 5 times 4 is 20. That'll go into 120 6 times. So that'll leave me with a 6 up there. I mean, at this point, you could just pop this into the calculator. So I've canceled those with that, leaving me with a 6. I know that... What else do I know? I know 3 goes into 117 by my dividing by 3 rule. So, you know, this is getting a bit tedious at this point, but it's still doable. So that gives me 39, canceling this 3 with that 117. And then I know 2 can go into 116 58 times. And then there we go. That gets rid of all my fraction. So now I can just calculate what this is in the calculator. You don't have to go that far with the simplification. You can just, as long as you can get to this point, and then you can just pop all that into the calculator and then hit equals and then divided by, and then this, whatever this is, 5 times 4 times 3 times 2 times 1. Okay. And this, by the way, would equal, obviously, it would equal the same thing, 190,578,024. Okay, now I want to talk a little bit about how something like this could be important, relevant, very relevant in real life. And I'm just going to talk. I'm not going to write anything down for this particular idea I'm about to talk about. Okay, consider a company that has a diverse set of workers, okay? And let's just say it's split roughly 50% down the middle, male to female, okay? So we'll just talk about, just gender diversity, and just to make it easier, we'll just say male versus female, right? So let's say there's a company has 120 people, and there's 60 male, 60 female. And they do this. They actually choose a committee of 5 people, right? They choose a committee of 5 people from a pool of 120, and they say they did it randomly, okay? And this company, let's say this is like some representative group that's going to represent the company somehow, okay? But they all are male. All of the employees are male. So the women are justifiably upset if we assume that being on this committee is a good thing, right? So they say, we're going to calculate the probability. So the company says, oh, it's just a coincidence, right? It's just we picked randomly. It's a coincidence. And someone decides to actually calculate the probability of choosing 5 men from a group like this that has 60 men, 60 female. Like, what are the chances? What are the chances that all 5 are men? This, if you're calculating your probability, this number, this giant number, would be your sample space. It would be the denominator. The total number of ways to choose 5 people from 120 people is this giant, 190 million, blah, 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 blah. So if you wanted to calculate that probability that I just described, this would be your sample space. By the way, you can skip this part of the video if you're not interested, but what if, so I'm going off on a tangent here a little bit. What would the numerator of the probability be? What would be the event space? Well, the event space that we're measuring would be how many ways are there to choose, no, let me think. What would it be? Okay, so I think it would be, if we were looking at, so still going off on a tangent here, had to pause the video and have a little bit of a think about this. The number of ways to choose 5 men, like just 5 men, not, just all, men, would be 60 choose 5, or 60, well, I'm saying choose because that's another name for the combination function. I should say 60C5. which would be, if I asked the handy calculator, because this is how many men there are in the committee, or rather in the company, and we want to choose 5. So this is the number of ways to only have men in the committee, and we're getting 546. Oh, wait, no, I'm reading the number wrong. There's one more digit. 5,461,512. That's a lot, right? It's a lot. But what is the probability then? What is the probability of choosing? So what is the event here that I'm trying to measure? Choosing only men. This is going to be a long event. Choosing only men for a 5-person committee. Committee. Choosing only men for a 5-person committee from a group of 120 people made of 60 men, 60 women. That's quite an event. Typically what you would do is just call this like some letter, like capital E or something like that, and then you'd say P of E, just to make it easier, would be equal to this event space divided by this sample space. So 60 choose 5 over 120 choose 5. And this would end up being, if I just calculated that, with the calculator, 120, yep, 5, getting, and as a percent, so multiply by 100% to make it a percent, and I'm getting 2.866%. So, in a problem like this in the real world, if this sort of thing happened and the company said, oh, it was just a random coincidence, and then someone came at them and said, well, actually I crunched the numbers, and this is assuming I did this right. I actually had to have a good think about whether or not this was right. Pretty sure that's right, how you would do it. Anyways, if someone crunched the numbers and they found this percentage to be that small, then they would probably have a good argument to say, no, I don't think it was random, because that is a very, very small probability, right? Okay, that's enough of a tangent. Let's get back on track here. Oops. So my props there from last lecture. All right, 38 and 39 I've assigned as problems for review. So let's try, let's try 40. It says Avery was born on, what in the world? Oh, this is a repetition problem. Well, I mean permutation with repetition, my goodness. Let's not do that yet. Okay, let's look at number 41. Skipping 40. 40 is a problem that's, I'm going to try to not make us do those kinds of problems. It's called a permutation with repeated objects or repeated numbers or whatever. In the case of number 40, it was repeated numbers. And we can, possibly we may look at those, but I'd rather skip those. Any problems like that. And that actually reminds me, I need to go through the Hawks homework and make sure there are none of those. Sometimes they sneak in without me realizing. All right, let's look at number 41. It says there are 18 tenured faculty in the biology department on campus. The department needs 1 tenured faculty member to facilitate undergraduate research, 1 member to supervise graduate advising, and 1 to coordinate grant proposals. In how many ways can these tasks be assigned if a member may only be appointed 1 job? What do we think? Permutation or combination? I'm going to say order matters. Order does matter here. Because these are all distinct different jobs, right? They're different jobs. All three of these jobs: facilitating undergraduate research, supervising graduate advising, coordinating grant proposals. Those are all different jobs, right? So giving three people those three different jobs, you have a bunch of different options, right? Because each combination is different. So that means order matters here, which means that we're going to use permutation, and it's going to be 18p3, y3 because there are three different jobs, y18 because there are 18 faculty members to choose from. So we're getting 18 factorial over 18 minus 3 factorial, which is the same as 18 factorial over 15 factorial, which is just going to be 18 times 17 times 16. I'm running through the arithmetic pretty quick here because at this point we've practiced it a lot, and don't forget that you can always ask me during our meetings to actually work the math out. Okay. 42 says a service organization on campus needs a group of 6 students from their organization's membership of 123 students to serve as program attendants at graduation. How many ways can the attendants be chosen? Well, order doesn't matter here. I'll put it here. Because we're just choosing 6 students, and they're not 6 distinct jobs. They're just 6 jobs, or 6 positions, or whatever it is. So we're going to have 123 because there's that many students to pick from. Combination 6 because order does not matter. That's why I'm using a combination. It's going to be this. There we go. 123 minus 6 is 117. I know that that's going to make it so that, and I'm going to back my equal sign up so I have room here. The 117 and below will cancel, so I'll have 123 times 122 times 121, 29, and 18. There we go. And then that effectively cancels all of this out, and now I still have the 6 factorial though in the bottom. And then I'm going to say calculator. How do you do this if you don't have that NCR button on your calculator? If you have parentheses, you can do it like this: 123 times 122 times 121 times 120 times 119 times 118 divided by, and then start open with your parentheses, and then say 6 times 5 times 4 times 3 times 2 times 1. Well, times 1 doesn't matter, but oh well, it's already there. Close the parentheses. You have to wrap that product in the bottom in parentheses, otherwise your calculator will think that you're just dividing by 6 and then throwing the rest of the product up top. By the way, what are we getting? 424 9404082, so that number is, yeah, okay, 4,249,404,082 possibilities there. Okay. Now 43 and 44, they are both also that special kind of permutation. Let's see, I'm gonna go ahead and show you how to do it. Why not? I'll show you how, and that way if it comes up you'll know how to deal with it, but it won't be on the exam. Right, so this formula is going to be for things that are within the group things are repeated. So what is the formula here? Okay, so the number of distinguishable, meaning unique, permutations of n objects, of which k1 are all alike, k2 are all alike, k3, k4, k5, they're all similar to each other, and so forth, so all the way up to k sub n, is given by n factorial over k1 factorial. Now this seems very strange, and we'll say kp, not kn. That's right, yeah, it's not kn, but what we do have is where the sum of these things in the bottom, without the factorials attached to each other, or attached to themselves, is equal to n. All right, so this is, I'll definitely agree with you. It's a very strange, maybe hard to understand formula, but an example will help here. Let's look at that number 44 now. Or which one did I skip? Yeah, let's do 44. 44 is a good problem. It says, in how many ways can the letters in the word Tennessee be arranged? So let's write down the word Tennessee. 2 S's. Always have to, yeah, of course. Always have to think about that though. Okay. So the point is here is that we have repetition within the group itself, right? Like there's 4 E's, there's 2 N's, and there's 2 S's and 1 T, right? So that's going to be, that creates like this extra layer of complication. And to deal with something like this, where the question is how many ways can you arrange these letters, we can use this formula here, where n is going to still be the number of items in the group. So n would be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. K1, if I let K1 represent, so what is this? It's supposed to represent the categories of letters in this case. So T, then how many T's are there? Well, there's just one. So K1 is just T. T is not really the problem here, right? It's the other letters that are repeating. Let's let K2 represent E. Then K2 equals 4. Right, wait, 1, 2, yeah, 4 E's. Let K3, and I'm just going to go until I run out of things to organize. And then K3 equals 2, because there are 2 N's. And then finally the last letter is S. And there are 2 of those. So in my formula, I'm going to have n factorial, so that's 9 factorial over, and by the way, the sum of all these k values is supposed to equal n. So that's a good way to check and make sure you didn't miss any of the letters or any of the categories. 1 plus 4 is 5, plus 2 is 7, plus 2 is 9. Good, so I have this relationship holding. All right, and in the bottom here, I'm going to have k1 factorial, so 1 factorial, which is going to be meaningless, right? Then 4 factorial, 2 factorial, and 2 factorial, just by following along with this formula. That's going to give me, I'll just write it all out. 9's not too big, it's not gonna, okay, so 1 factorial doesn't matter. 4 factorial, is 4 times 3 times 2 times 1, and then 2 factorial is times 2 times 1. All the times 1s don't really matter, but there they are. Right, and what am I getting here? Let me cancel some stuff out. 4s cancel, 3s cancel, this 2 cancels. Oh, look, and 2 times 2 cancels with, oh, never mind. Oh yeah, 2 times 2 is 4, so it can cancel with that 8, leaving me with another 2 up here. So I have 9 times 2 times 7 times 6 times 5, and all the times 1s don't matter. And that's giving me... So there's not a button on the calculator to do this. You've got to clean it up and deal with it like that. So, of course, at this point, I can bust out the calculator and ask it to do this last step. $3,780. All right. This is probably the most complicated things can get. When you're trying to organize, you're rearranging things, or letters or numbers typically, where the letters or numbers they actually repeat. There's more than one of multiple types, and in that case you have to use this formula. So numbers, if you'd like to have a little bit more practice with this, number 40 and number 43 also require this technique. So in this lecture, I didn't go over the actual examples that remained, but we can definitely save those for the in-person talk. So from the text, example 4, 5, 6, and 7, 7 being another one of these repetition type things. So 4, 5, and 6 in particular, we can look at those in the actual class lecture. All right, that's it for 7.2.